Okay. So as I said, it's one of the fundamental parts of computational thinking. It helps us so that we can make our computer systems more efficient, easier to code, easier to fix. But it's also a skill which is useful for anybody, not just person in computing. Pattern recognition is shown here as the fourth of these four different, very important foundational parts of computational thinking. And I hope that you can see these diagrams actually mean something. I hope that you can see in this diagram that our pattern recognition, you can see the pattern there, right? You can see the pattern here in sort of like die. They look like die that you throw in a game, right? But being able to see the pattern allows you to make recursive programming, to make modules, to make iterations. It's very, very useful. Here's an example of an iteration, right? An iteration is where you repeat some part of a program code more than one time in order to do something more efficiently. So, I could, I suppose, pull that out, but this is fine for now, I think. So some examples of patterns. Any of you guys ever done an IQ test? Yeah, some people like to think, oh, because this thing about IQ, 50% of the population sort of have an IQ somewhere between 85 and 115. And if you got an IQ of more than like 160, you're like some genius person or something like that. But if you got an IQ of like 115, you can sort of do technical jobs pretty good. So, and you can go to university or college or whatever. So the IQ test, if you do one, usually they'll give you 20 or 30 or 100 questions, and there'll be questions like this. And so they'll say, okay, find the pattern. And so can you write the formula of the pattern? So you'll look at it and you say, oh, that's just like maths. Why is IQ math? Well, it's pattern recognition is supposedly something that relates to a person's ability to function sort of cognitively. And so that's why you do it in the IQ test. And I hope that you can see here that there is a pattern. If you look at that carefully, most of you will see that without having to apply too much mathematics to it, that there is a pattern to it. And actually the mathematics is kind of simple. You add 4 to the preceding number, and that gives you your number, right? So 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is, yeah, you get the idea. And the next one, again, there's a pattern. And if you looked at that from a fairly basic mathematic mind, you'll see that you multiply by 3, right? So you guys are passing the IQ test. There you go. Multiply by 3, and you get the next one. The next one's a little bit trickier. It's not that tricky. It's actually called a Fibonacci series. Very easy for people like me. I'm not saying that I have IQ. No, that's what I was saying. So it's because I've done some computing, and we use this all the time. It's called the Fibonacci series, and we use it to teach recursion. So recursion, what you do is you have a big problem. You break out the smallest part of it, and you repeat it within itself. You repeat it within itself. That's kind of weird. So what you might notice, there should be a number 0 at the start here, actually. But what you might notice when you get to the third number is the third number is the sum of the 2 numbers before it. The fourth number is the sum of the 2 numbers before it. The fifth number is the sum of the 2 numbers before it, etc. And so that's the Fibonacci series. Again, so again, here's another pattern. And actually, as I said, the IQ test, they show you stuff like that, right? Show me the one that's wrong or something like that, right? Can you solve the Tetris? You guys ever play Tetris? Yeah. All right, so that's a pattern. Can you recognize the pattern? Could a computer recognize the pattern? Is there something there repeating? Yeah, wallpaper, right? Any of you ever had wallpaper in your house? That's the first thing you do is look in there. Can I see the pattern? And so you need to be able to see the pattern to hang wallpaper properly, because you got to get it matched up so that it doesn't look like it's a pattern. Anyways, this is a pattern. Okay, that's kind of a weird pattern, but if you worked in an office where you're buying and selling things, you'd have to recognize this pattern. If your boss asked you, what is the sales tax on that invoice? You might have to study it, right? But pretty soon you'd recognize the pattern. You'd know exactly where to look, and you could find that sales tax within just a second or two, right? Because you would recognize the pattern. And that's why people, these kind of jobs where you're doing that kind of thing, when you first go and do the job, you know, for the first week, you're a little bit slow, but after a couple of weeks, man, you just get really fast at it. It's not because you got any smarter. It's just because you recognizing the patterns, right? So in almost all of our work that we do recognize a lot of patterns, and it makes us faster. It makes us more efficient. So the idea here is that within a particular problem, you may see a pattern repeated, or you may see a pattern repeated across multiple problems, but it seems to be the same pattern. So can we see that here? Well, maybe. When you analyze a problem, you can work on its solution. That makes sense. And if problems are similar to each other, then maybe you can borrow or reuse some of your other problem-solving solutions. We do that all the time in computing. Now, when you start computing in a programming language like Python or Java or even JavaScript, you'll be presented with libraries. Have you guys heard of this kind of thing? So what are libraries? What they are is they're the problems that keep coming up over and over again. And so somebody writes a really good answer to that problem. A library is actually a compiled and solved computer program that's just been put away, and you just can go and grab that library so you don't have to write the little program. So you can insert somebody else's program into your program. That's how the library works. And so we recognize, that's a pretty common problem inside my problem. I'll bet there's a library solution for it. Yeah, probably, especially if it's in Java or Python or something like that. There's pretty comprehensive libraries for that. All right, so here's an example of that, right? So an athlete throws a discus. A discus is a round, like a plate, that the athlete will swing his body or her body and then release the plate and see how far it'll go. And it's weighted. So it takes some strength and some little bit of skill. You have to learn how to do it. But a lot of it is really the strength. How far will that discus go, right? And so by measuring the distance of every time they do the throw, it gets an idea of how good he is at it, right? And so you might want to know an average. Average is quite useful. How we do an average is we take the total of all of the attempts or all of the values, and then we divide that by the count of all of the values. Very simple average. You've done this, right? And it is a number which we can use. It's quite useful. Now, this athlete's only done this 3 times. On the other hand, the meteorologist is measuring the temperature every time for an hour, every hour, sorry, for every day of the year. The meteorologist wants to get the average. But they're exactly the same problem, are they not? Right? Again, you're just going to add up all of the values and divide them by the count, and you will get the average. So you could create a little solution to that, which is calculate the average, which is record all the values and have your little program add up all those values and divide by the count. Any of you guys use Excel? Yeah, so if you use Excel, you can have a list of values, you highlight the values and you press on you've got a little formula button in Excel. Press on the formula button there that says sum, and there'll be a thing there saying average. Why? Because it's such a common problem, right? Everybody's doing average all the time, so you don't even have to do it. You just go up there and press on the button, there's your average for you. So thank you, Excel, for that, but they're not the only ones that do it. You can also find average functions in SQL programming language. And it'll be in one of those libraries for Python and Java. What do we got here? So yeah, there would be a math library in Python and Java, which will have common math functions in it. Patterns inside a problem. So customer wants to mobile application to register their account. Here's another situation where somebody is also registering an account. So registering an account, is that the same problem? It's not going to be exactly the same problem every time you register an account. Registering an account with Rito, registering an account with who else provides the service? Karawa or yeah, Vodafone. The process is going to be kind of the same. Every time you register to use an app on the computer, you probably do something very similar. And in fact, a lot of them will have, Google figured this out, right? And Facebook figured this out. And so you have a button there where you can just create an account by pressing the share your Google information, right? Or share your Facebook information. And so you can create an account that way and log in with it. So that's an example where they actually understood that this is a problem that everybody has. People don't like, typing a lot. So they like to press a button that just gives the information that's required, which is going to be the same every time, right? Name, probably your age, some kind of email contact, and maybe a password or something. But passwords now we're using, talking about pattern recognition. Our password. So for me, on my password, and probably there I have this thing that looks like a thumbprint, right? And I put my thumb on it, and then that's a pattern recognition. It's recognizing a pattern there, which is different than your pattern. So could you have a problem where you had to draw a polygon? These are called polygons. The simplest being a triangle. We're going up to a, how do you say that? Decagram. Nonogram and decagram. The thing before the ogram is how many sides it's got. So triangle's 3, decagram's got 10, octagon, etc. So could you could you break that down into, can you recognize a pattern if you had to start at one point and draw it? I think what you'd do is you'd recognize that, all right, so a triangle's got 180 degrees in it, right? So what about this? That's 90, 90, 90. That's got 360. I think these others, and what about these? Those are bigger than 360. So for the triangle, it's easy because you'd start and then you'd go in a direction. You'd measure your angle. Sorry? Sorry, I can't hear you. Which one's 70 degrees? That looks like more than 90. Looks like 120 or something. So that's why I'd say it'd be like, so this is 360. I think we're getting to pretty high. I don't know the math on it, but if you could calculate a distance and then calculate an angle and then use a vector, you could draw these. For the triangle, it would be easy because your totals has to add up to 180. For your quadrangle, it's going to, or rectangle, it's going to add up to 360. I think these numbers are bigger than that. I think that's bigger than 90 degrees. So I think that's like 100 and something. And so it's going to be like 500 or some big number. So yeah, I mean, I haven't done the math on it, but you could do the math on it. You could work out the angles, and maybe you could even have that stored in a table. And then you could calculate and do a vector, to get it in the right place. Here's a more simpler one. What if you wanted to draw this? Now, this is not drawing all these things. It's drawing this. You just want to draw this shape, which is like somebody's face, sort of, with some missing stuff, like a nose. Right. So that's like the simplest face you could get, I guess. And what's simple about it is everything represents either an arc, which is part of a circle, or a full circle. Right. We got it. This one here is the only one that's not a full circle. It's an arc. And so if you could draw a circle, you've already got to start on drawing this, right? So then the other things you need to know is where's the center of the circle, and what is the diameter of the circle, and what is the thickness of the border, and what is the fill. So if you knew all those things, you could go ahead and draw this. Now this one here is just like a half circle, so you'd have to know to stop when you got to halfway drawing the circle. If you knew all those things, you could do it. So the main skill that you'd have to teach it would be to draw a circle. And so these are things you'd need to know. What is the diameter? What color is the line? How thick is the line? What fill? If you're going to use a fill. And the size of the cut, I guess, is how many degrees out of the 360 will you go before you get there? I mean, here's another simple one that you could do by breaking down that problem into small ones. Draw a couple of circles. You can draw some crosses. You draw some rectangles and a triangle and some cloudy thing. You could do that with circles, right? A circle there overlapped with a circle there, with a circle there, with a circle there, with a circle there, and then fill it in, and another rectangle. So if it's some fairly simple programming, you could probably draw that one. So yeah, you're gonna need to be able to draw a rectangle. We talked about that. You're gonna need to draw a. So I did not make these slides because border is not spelled with an A. Border is spelled with an A if it's the person that lives in your extra bedroom. That person is a border. But if it's around something, it doesn't have an A. All right. When you decompose a problem, you find patterns. Hopefully we see patterns. Now, what you're going to see, I don't know if I'll, yeah, we got 2 hours today. Ooh, it sounds ominous, doesn't it? We've got this little programming language that's called Blocky. And there's a free website for the whole world. I mean, that's amazing, right? You just register it. It's like, I don't know, some people in the US do it actually, but it's called code.org. And you guys are going to go on there and you're going to do this stuff and you'll be able to see, hopefully as you do it, you'll be able to see patterns, and so that you can start doing repeats and stuff like that. But I'm hoping I have enough time to show you that today. So a subroutine, you would have a subroutine for a circle because you're using that all the time, right? So here we have a subroutine, it's called circle, and you see the things that we need. These are the parameters that we use for that subroutine. So we got a parameter for the, I guess that's the center, which is going to be XY on the map, the diameter from the center, the border who doesn't live in your bedroom, the fill, and how much of it you're going to cut. Yeah. Okay. Now the spelling, I was making a bit of fun on that, right? But the spelling, you do need to be familiar with American spelling. Okay, so you do need to know the right spelling of things like borders and color and stuff like that. You need to know the American one, not the British one. Why? I don't know, because the people who wrote all these computer languages, I guess they're over there in San Francisco or something, and they spell stuff in the American way. And so if you spell color with a C-O-L-O-U-R, which is correct where I live in Australia or Canada when I'm not here, but it doesn't work on a computer, right? So remember, you just sort of keep an eye on that kind of stuff. So subroutines, they're keystone programming languages. The idea of subroutine, I think I've made this before. We call it's part of what we call software engineering. And I'm sure you've heard that term, right? Now, there's a big history that goes into that, but basically, people who used to write computer programs back in the 50s, 60s, 70s, they were kind of artists almost, right? I mean, they're very creative people who would write this, creative and smart, mathematical, but they would write programs, and it was like a craft. So what I mean is you could look at a program and you kind of tell who wrote it because of the way that they would put the construction together. But the other thing is that everybody's was kind of separate and different, and it wasn't reusable, and it was very, very hard to fix it. So when you got bugs, and you always get bugs in programs, when you got bugs, it's kind of hard to fix it. So what happened in like the 70s, 80s, 90s is people doing software development, looking around the world, and what they see is they see the way engineers do stuff. And they realize, well, look, there's some of the things that engineers do that would really help what we do. Maybe we should take some of those ideas. And some of those ideas were things like reusable units. All right. So if you go and look at a car, cars are engineered, right? Pick your car. I don't know. So I'll just think Silverado because I like those because I got one of those. But every wheel on the Silverado is interchangeable. You know what I mean? You want a wheel? They're all the same. You know what I mean? I can take my wheel off my Silverado and give it to somebody else who's got a Silverado, and they would be able to use it. I can find lots of those wheels everywhere. Now, if you take this to the furthest extent, like Toyota does, they start with their really winter vehicles, which were the 4-cylinder little pickup. What's that called? The little Toyota pickup. They use the same engine for a long time. Why did they do that? Because they're stupid, right? They can't come up with a new engine. No, because they got the engine and they made it right and perfect. And so it has all the reusable parts. You can find these parts anywhere, right? And they're cheap, the parts. And so this vehicle will go forever. You can buy this Toyota, what do they call it? The little wagon, the little pickups. Oh, I don't know. But obviously I don't have one. But I mean, the design idea is that you can have this vehicle, you can treat it badly, hardly ever do much maintenance on it, and it'll still last for 25 years. And you can find parts anywhere. And that makes it because so people buy it. So a lot of this, all right, that's a great vehicle. That's engineering, right? The parts on that engine work on other engines that Toyota has. And you might say, well, why is Toyota's engine 10% less powerful than the Nissan comparable one? Yeah, it is. It's not as powerful, but it'll last longer, 30% longer, because they didn't mess around doing new stuff. They got something that worked. They got replaceable parts, and away they went. That's called engineering. So that engine that I was referring to, I can't remember the exact number from it, is UZ something or other. It's been around for 50 years, and all they did is sort of just tweak it. And it's awesome. It's a subroutine. You can keep using it over and over in every vehicle, right? And yeah, so there you go. That's what we mean. We get something, we get it right. In computing, what we do is we stick them in a library that I was mentioning, right? So you got this perfect little code that works. And so why am I going to go and spend all the time to figure that out again? I'll put it in a library and I can use it again. And so can my friends. Now, when I say so can my friends, I'm sort of alluding to the fact that a lot of computing nowadays, and it is engineering, a lot of computing nowadays is open source. So if you use Linux or you use the LAMP stack for development on the web, so that's Linux and Apache. What else we got? We got MySQL and PHP. If you use that, that's the LAMP stack. All of those things are open source, which means they're developed for free. You can download them onto your computer and use it all free. And it's supported by everybody who uses it using engineering principles. And so you have this code that really works really well. And you have libraries that are kept up to date and work really well. So that's engineering. Software is kind of cool for that, right? So this idea here is that when we have a big problem, what we do is we go and look at what the solution should look like, and then we step back from that and we can see what we should do just before we get there. And then when we figure that out, we can go back from there. That's the stepping back thing. It's okay as long as the goal state is well defined, which is a good thing to do in computing, because that hasn't always been the case. Pattern recognition again. So we're going to kind of finish up on pattern recognition, I guess. So with some very, very good computing, you can recognize the face of a cat, I suppose. You can recognize the face that is a cat. So you can categorize the cat. Categorize the cat, yeah. So in other words, you can tell the difference between a cat and a human. You can tell a human from the background, right? So that's what these squares are. And you might have noticed that when you pick up your camera and you point it at your friends, right? A bunch of square boxes go around, right? Who's this, who's this, who's this? Because what happens is the software in your phone, the camera has recognized that that's a human face. And then supposedly you should know that person. Now, when you use your phone again, you can switch on a security aspect, which will recognize your face, so that only your face will allow access to this, or only your thumbprint, right? So with the face, you might say, oh, well, so it's not even looking at, your color, because that's going to change from day to day and, depending on the light. So it's not going to look at that, but what it's going to look at the things that never change. And so what are the things that never change? Well, the distance between this part of your eye, of your eyes and that part. And not only does it never change, but it's different in every person. So that measurement, if you took that measurement with me, that'd be different than for you. And also the measurement from there to there, that would be different, and et cetera. So you got, like, as you can see, there's, I don't know, it looks like 20 or 30 little points that they would measure, and they would measure all the distances, not just one distance. They measure all these distances, distance between there and there, distance between there and there, all those distances, measure the distances. And just by doing that, they can tell that's your face, because nobody else is the same as that, not even your twin brother, apparently. but maybe. All right. So that, and so you know what I'm saying? I mean, even me with my beard, I should be able to pick it up. But, well, the problem is we wouldn't be able to measure these ones, right? But you know, that if it had enough data from the other ones, it'd be able to pick it up. So that's kind of cool. That's pattern recognition. Now, this one here, right? It's probably worth mentioning, right? So during the COVID thing, I think I mentioned this to you before, right? We've got SRS on here. And they got something like that in China. They got SRS in there. But the other thing they got in China is they got cameras everywhere. And so when you walk outside, what it's doing is, oh, there's Mark. Oh, Mark's not supposed to be outside. The police come and tap you on the shoulder and take you away, right? So I don't know. Think about that. And that's the end of that one. I mean, yeah, I think that I read something, and this is like 10 years ago, that your average person walking around the streets of London, England, so not even China, right? London, England, shows up on a closed circuit TV, CCTV, they call it, right? On a camera about 350 times a day. So they're watching you in London. I don't know if they're watching us here, are they? Maybe, I don't know. Don't do anything that you don't want your mom to know about. So yeah. Or the rest of the world on Facebook or something. I'm just going to take a note of who's here. Or the CID. Don't do anything. More important, right? Don't do anything you don't want the CID to know about. Okay, so how are you feeling? You think we can continue on a little bit more? I got a couple more of those to show you. Is that all right? That was the lecture that I was supposed to give you, but I don't want to sort of let you go just yet, because there's a couple of other things that we could look at. Now, this one here, we did the abstraction and modeling last time, right? So that's there for you, and I'll let you look at that. But so I won't go through that, but I put it up there again because there's a couple of new slides in it. But I won't go through it all just for a couple of new slides, but I recommend that you guys look at it. Somebody's trying to talk to me on the chat. They're probably going to say that the time is running out. That's correct. So what are they saying? My name is not iPhone. Okay. Don't put anything on social media that you don't want other people to read. All right, so go to this thing here called code.org at some point at your leisure. Maybe you can do that during this lesson. And when you go there, code.org, I gave you the link, so it'll take you straight there. Now mine says sign in because I have created an account. You need to create an account, right? So I'm not sure what the button is, but it's going to be something like that. You'll create yourself an account. Now it's not this create. This create is create some learning module. But you need, so I think where the button says sign in, you'll have a thing there called create an account. So I want you to create an account there. When you've done that, I want you to go to this, follow this link. And this link is unique to our class. Okay, this link is unique to our class. So if you follow that, it'll ask you to join the class. Yeah, okay, so I'm sorry, because it's your first time, right? So you log in with student as your name, and the thing is 1, 2, class 3, 4, right? With the exclamation mark? Oh, hold on, this is a production lab. This is not a VPN lab, sorry. Yeah, you log in with your student number. and you have your own password that you may have set. No? Okay, so that's a matter of going and talking to the IT people. Yeah, the one that you use for everything. So if you follow this thing, this link, it should get you to code. I'm just going to go back here because with code, oh, will it? I'll sign in. Yeah, that'd be a good idea. So once you've created it, did I sign in with Google? I think I might have. Yeah. And so what it's going to do, it's going to ask you to join a class. Here's the two classes I have. I see that I've already got 2 people from this class have joined this class. So I'm going to ask you to join that class. When you do that, you are automatically put into this course, which is called Express Course. Express Course is this course here. Now, I've been doing a lesson on that, so I'm just going to open it up. So you have a video when you start the course. You have a video that tells you kind of what to do. And then you have a lot of lessons that go with it. So this one's got like 13 lessons, but the lessons are kind of short. So let me just give you an example of one. Practice, challenge, I don't know. Number 7, let's try that. Lesson 7. So lesson 7, I've already done it. Okay, so I want to be culturally sensitive here. So I want to tell you, I did not make this game. They put in there a haram animal, but it's okay. It's not about eating it. It's about blowing it up. All right. So it's about kicking out the haram animals. Okay. We use a bird to remove the haram. Is that fair enough? All right. Yeah. Take a haram situation, make it halal. Correct? There are 3 options. Facebook, Google, or Microsoft. Yeah, you could use your own, and then you make your own password. I think said that 4 times now. When I looked at it, it said to ask your students to create their own password. All right. So if I run this, you'll see how it runs. Now, then what's more interesting, I think, from our point of view, is before you leave, if you see something like that, have a look at the code. And can you see this, right? So these are functions that work in a programming language. I think this is JavaScript. Looks kind of Java-like in JavaScript. In fact, I'm pretty sure I read something about it was JavaScript. So what we've got is we've got a turn left, move forward, turn right, and then we've got a repeat. Now, the way that this repeat is structured is in the for statement. This is the way a for statement looks in Java, and I guess in JavaScript as well. So how it works is we initialize a count variable. Initialize, we give it an initial value. Give it an initial value of 0. Now, you don't have to write this code, right? I'll show you how you do it on here, but it's nice to look at it because one day you will have to write it. Maybe one day soon, like next semester or something like that, when you do a JavaScript course, which you're not doing now, but so, you don't have to do it now, but it'd be nice to know when you do have to do it, right? So get used to looking at it. That's what I'm saying. You do not have to write any of this code in this course, but I think it would be really good for you to look at it and sort of say, okay, so how does this work? For loop repeats. Well, it has to repeat a number of times. Well, how will it know a number of times? Well, you initialize it, 0, and you keep going until you get to 3. 0, 1, 2. Yeah, you can't go to 3. So you're going to do it 3 times. 0, 1, 2. And this means to increment or to go to the next one. So if you started at 0, this will make you to 1. Then if you're at 1, this will make you to 2. So that, and then what happens? This is in part, this thing is part of the for loop. So what it's doing is it's moving forward 3 times. That's a nicer way of looking at the code than just go move forward, move forward, move forward. Move forward 3 times. We saw a pattern. The pattern was move forward, and we repeated it. That's what happened there. Okay, so that's puzzle 7. So let's, oh, come on, let's break the puzzle. This one's got lots of bugs. Let's break it. Yeah, really? Okay, we'll break it like that, right? So can I throw that in the rubbish? Won't let me. Take it apart one bit at a time. Oh, well. Anyways, if I try and run it now, it'll only move forward once. That's all it does, right? Because that's the only thing that's part of the code. Keep coding. Something's not quite right. Yeah, you're right. Now I could put that back and it might work, but it looks like it won't. So what I'll do is I will look at it and I'll try and figure out what's going on here, right? Can I use that? Can I throw that over there? Yeah. Go, get away. So obviously I haven't figured out exactly how to do that right. But what I can see is I can see what you need to do to get this to work. So, right. So what we've done here is we said move forward, turn left. Move forward, turn left. That wouldn't work. We would have to turn right. Right? So start, because the starting position is going to be here. When I reset it, the starting position is going to be there. Move forward, turn right, right? Then I'd have to move forward again, right? That would get me to here. Then I'd have to turn left. Got to turn left there. Yeah, I'll use this one. Move forward, turn left. So that would get me from here to here to here, to turn left. Then I'm going to do another move forward. That would get me there. Then I'll turn right. Now I'm going to move forward 3 times, right? 1, 2, 3. So that's why I do this repeat thing. So the repeat thing, you can say the number of times here. 3 times.